All right, so I linked a video on conduction, convection, and radiation, but the one we're going to deal with in problems is conduction. So conduction is when thermal energy transfers from a hot object to a cold object by direct contact. So literally the hot molecules are hitting the cooler molecules and transferring energy, and it transfers through the object. So the example I want to have is we've got two pots of water. The one on the left is boiling, so it's 100 degrees Celsius. The one on the right is a mix of ice and water, so it's 0 degrees Celsius. And we have somehow connected two solid rods between the two buckets of water so that on the left, the rod is going to be at 100 degrees Celsius. And on the right, the rod's going to be at 0 degrees Celsius because it's in contact with the water. And the question is, how much heat transfers through those two pipes? So the top pipe is going to be made of stainless steel, and it's got a 2 centimeter diameter. And the bottom pipe is going to be made of copper, and it's got a 1 centimeter diameter. I keep saying pipes, but they're not pipes. They're solid rods. We don't have any water flowing through the solid rod. What we have is thermal energy flowing through by conduction. Okay, so what would affect how quickly the heat travels through these rods? This would be a fun exercise to do in class, but I think we can sort of imagine that if you had a larger, fatter rod, that more heat could travel through it in any given period of time. So the cross-sectional area of the pipe or the rod is going to play a role in how quickly heat can transfer through it. Also, the temperature difference between the two sides of the rod is going to play a difference in how quickly heat transfers through it. And I think that makes sense. If the left side was 200 degrees instead of 100 degrees, there would be more heat flowing through the rod more quickly, more thermal energy flowing more quickly. Okay, what else would matter? The distance that the heat has to flow. So in this case, that would just be the distance between the two buckets of water. If that distance is large, then the heat would flow more slowly. If that distance is short, the heat would flow more quickly. And then finally, the material, what the rods are made of, is going to have an effect. If you have a wooden rod, heat would flow very slowly. If you have a gold rod, heat's going to flow more quickly. We know that metals are good conductors of heat, and things like styrofoam are bad conductors of heat. And all of that plays a role in the constant, the thermal conductivity of the material. So now we can probably create an equation that we would like to have for how quickly heat transfers. And here, P is dq dt. It is the rate at which heat is traveling through the object. And of course, that's going to be measured in watts, joules per second. Okay, and so a larger area should make for more heat transfer. So we're going to put area in the numerator. A larger delta T would make for more heat transfer. So we're going to put delta T in the numerator. A larger distance would make for less heat transfer. So we're going to put D into denominator. And then where we put K just depends on how K is defined. And K is thermal conductivity, meaning the bigger the number K is, the more heat flows through the object. So K goes in the numerator. And if we look at this equation, we can see that the units for K have to be watts per meter degrees Celsius. And the reason is, if I start with watts per meter degree Celsius and I multiply by area, I get watts meters divided by degrees Celsius. Multiply that by delta T, I get watt meters, and then divide by D, I get watts. So power should be measured in watts, so that's the right unit for thermal conductivity. Okay, so now if we just knew the thermal conductivity of stainless steel and copper, we could figure out how quickly heat is flowing through these two pipes. And for fun, then we could figure out how quickly the ice would be melting. So we're going to assume that this thing is on a burner so that it maintains 100 degrees. And because we've got a mixture of ice and water, that's going to maintain 0 degrees, but the ice is going to be melting as the heat is transferred into the ice water. So let's first figure out what the power is for each rod. The stainless steel rod has a 2 centimeter diameter and the copper rod has a 1 centimeter diameter. Okay, so the power is going to be the thermal conductivity, and let's do the power for the stainless steel first. It's going to be the thermal conductivity times the area of the rod, and for this that's going to be pi r squared, so pi times 0.01 squared. We were told the diameter is 2 centimeters, so that means the radius is 1 centimeter, or 0.01 meters, times 100 degrees Celsius, because that is the temperature difference, and then divided by 0.05 centimeters, because that is the distance that the Q has to flow, that the heat has to flow. Likewise, power for the copper is going to be whatever the thermal conductivity is, times pi times, again, the copper now has a 1 centimeter diameter, so the radius is 0.005 meters squared, times 100 degrees divided by 0.05. And now we just need to look up the thermal conductivities. So I go to the textbook, and for stainless steel, the thermal conductivity is 14 watts per meter degree Celsius. And apparently that's a relatively large number because we know that metals are good conductors. So then we look up copper, and we find out that it's 390. Now, what does that mean? That means that copper is a much better thermal conductor than stainless steel. Okay, well, now that we've got all our numbers, we can plug these in. I've already done that. You go ahead and check my calculator work, but when I plugged this in, I got 8.79646 watts for the stainless steel and 61.2611 watts for the copper, and that is a total of 70.0575 watts total heat transferred between the two pipes. So that's 70 joules every second. All right, now normally we would say that the heat required to melt ice is equal to the mass you want to melt times the latent heat of fusion. But if we want to know how quickly the ice is melting, if we divide, or if we basically divide both of these by T, so Q over T is equal to M over T times LF, the latent heat of fusion. We could even think of these as rates, like dQ dt and dm dt. How quickly is heat flowing? That's my power. That's what I just calculated. And how quickly is the ice melting? That's going to have units of kilograms per second, and it's going to tell me how much ice is melting each second. So if I want dm dt, that's just going to equal my dq dt divided by the latent heat of fusion, so that's 70.0575 watts divided by, okay, and I need to look up the latent heat of fusion for water, 334,000 joules per kilogram. And watts, of course, are joules per second. So the joules cancel, and I end up with kilograms per second as my units, as expected. And this is a very small number, 0.00021 kilograms per second. So, okay, so that's a very small number, but I guess we're not going to let this thing run for just 1 second. What if we let it run for a whole minute? Then I could multiply this by 60, and that 0.00021 is actually 0.002. Shouldn't keep poorly rounded off numbers in the middle of a problem. 0.000209753 kilograms per second. Okay, so if we wanted to run this for 60 seconds, we could say, all right, well, that means that 0.012585 kilograms per minute melt. And now to round to a reasonable number of significant digits, again, I didn't set up this problem very well. It's not clear from the problem how many significant digits we should have, so I'm just going to use 3. This is about 12.6 grams of ice per minute are going to melt if we have this set up. And of course, that assumes that there's no other source of heat for this water. It assumes that that this thing is inside of a very good thermos that's preventing any heat from conducting from the air around the glass or from the table underneath the glass. This is just the ice that would melt due to the heat going through the rods. All right, so that is conduction, and I think that's my last video for this week, so I'll see you in class.